Hey guys, welcome back to my YouTube channel. I am here with another video about coding, but unlike other ones, I will be talking about algorithms and programs that I did not make. If you like my video, please like and subscribe, and let's get right into it. In this video, I will be talking about two algorithms for text compression and discussing which one is more efficient in terms of space or bits saved. Let's get started with the less efficient naive algorithm. Essentially, this algorithm is called disemvoweling, and it removes all the vowels from a given string. You start with your string and loop through each character in your string. If this character is a vowel, you remove that index from your string. Let's go through the process the way a computer might do this. Save your string into a variable and create an index tracker that is set to 0. Then, loop through each index. If that index is a vowel, it removes that index and subtracts 1 to the tracker. Outside this if statement, add 1. This counter ensures that if an index is removed, it does not skip over the index it is replaced with. What about a more complex and more efficient algorithm? This is called a Huffman algorithm, and it was invented by David Albert Huffman in 1952. You have your input string, and you go through each character in the string. If it is a new character, it sets its frequency to 1. If not, it adds 1 to its frequency. Create an array with your characters and order them based on their frequency, from least to most frequent. Take the first two nodes with the least frequency and add their frequency into a new node and place them in the array where the element's frequency before it is less than it and the next element's frequency is more. Repeat these steps until you're left with one final node, and this is the root of your Huffman tree. Usually it looks like this. At the end of the tree where the characters are located are called leaf nodes. Now you can use this tree to encode and decode your string. To encode a given string, a function can be created that takes two inputs, the root and an empty string. To encode your string, you need to use recursion. In this function, if the root node has children, the function calls on itself. Since the first line calls on itself with the left branch, its new input is 0, and we go back to this line here. Since it does not satisfy the if statement, it will call on itself again. Since the left branch is first, it will call on left branch again, and now we have 0, 0 as its inputs. Now, since this node does not have any children, the string as the input will be saved along with the character. Now that leaf node is resolved, it's finished its life goals, and it will go back to 19. And finally, the function will call on itself with the right branch as input and as 0, 1 as input. This will occur until 36, or the root has completed its life goals and seen its children, grandchildren, and so on complete their life goals as well. Okay, take a deep breath. We are done the hard part. Now time for the function to decode the string along with the root as its inputs. In this function, make a new empty string that will have our decoded message and a new variable that is set to our root. We will then loop through each element in the encoded string. If it is a 0, we go to the left branch, and if it is 1, we go to the right branch, and if it's a leaf node, we add that character to our new string and set the current node back to root. Comparing the compression ratios of the two, we see that they are 183 over 288 and 192 over 288. Both of these numbers are quite similar, but in fact there's a big issue with the disemvoweling algorithm that turns people away from using this algorithm seriously for text compression. An important feature of disemvoweling to note is that you can't read it. I mean, unless you can, but you have to admit, it's pretty hard to read. So imagine you're a programmer, you want to compress your string. You're given a couple options, the ones that we were just talking about, and you want to decide what's best for compressing your string. A, do you choose the lossy compression for your text? That does make the amount of bits needed to save your string shorter, but you can't really read it. Or B, do you choose the lossless compression that can decrease the amount of bits you need to save your string, and it can reverse these changes? Or C, don't compress your string. Well, a programmer may make this decision depending on the text they would like to compress. Although I feel like we can take disemvoweling out of this, the reason being that it is what is known as a lossy compression, meaning when compressed data is removed, it is not recoverable, and while this may be okay for images, it is not ideal for text compression. On the other hand, the Huffman algorithm is lossless, which means the file size is reduced, but the original data can be reconstructed. In other words, the compression is reversible. But let's say this programmer wanted to compress the string high. The amount of bits to save this string would be 16 bits before compression. However, after compression using the Huffman algorithm, it would be saved with 18 bits. So this programmer may choose option C. But with the example that we have been using throughout the video, option B would be the best option. Thank you so much for watching this video. If you liked it, please subscribe and click that like button for more content like this.